Yo, what's up guys? So today I want to bring you guys a tutorial on how you can code your own queue data structure in C. So if you've watched my previous video on how to implement your own stack data structure in C and you understood the video, this is going to be a little bit easier, but I'll explain it from the scratch as well. We're going to use pretty similar concepts. We're also going to use linked lists to implement our queue. So we're going to implement a simple queue that has a initialize queue method, a free queue method, so we can free the queue memory, an add method that adds an element to the end of the queue, remove element removes the first element of the queue. So this is the main difference. So when comparing to stack, a stack is a LIFO, so it's the last in first out. A queue is FIFO, so it's the first in first out. And we're going to remove the first element instead of removing the last element as we would in stack. In peak here, it is the same thing, so we just return the first element of the queue. Clear, we're going to remove all elements from the queue, and we're going to have a print queue method that helps us visualize the queue in a certain formatted way. So as we stated before, we're going to use linked lists instead of arrays. So just to recap here, an array is something like this, where you have a contiguous piece of memory and you have a pointer to the first element in the array. So this has a memory address, and to access the next one, next index, you just add the size of the type the array is storing. So it's not that hard to access index values. So you just keep adding things. So adding things to the end of the array is pretty easy, but adding things to the start of the array is pretty consuming in terms of time, because you have to shift the whole array before you insert the element at the start, or remove element from the start as well, because you would have to shift back all the whole array. So that's the main reason why we're going to use a linked list here, because it's easier to implement a queue of linked lists. Might not be the most efficient way, but it works. So this is what I'm going to show you guys today. So a linked list is quite different from an array in the perspective, in the sense that instead of holding only a value, and you can just, instead of adding the size of the element, the size of the type that you're storing the array to reach the next index. In here, you don't have the idea of indexing. You store a value, so this is a value, and you store a pointer in something in a data structure called a node. So this is a node we're going to use on our linked list. So essentially this node here stores two things: the value you would want to store and the pointer to the next element, to the next node. So imagine this is the second node, it has a value and a pointer, and this is the second node. And you cannot, they're in completely uncorrelated memory addresses. So in order for you to reach the next element, you have to travel through the pointers. So you have to iterate through the whole linked list until you reach the next element. And if you want to reach the last element, you cannot simply index the number of elements inside that linked list plus the type of the element stored in the linked list. You have to loop through the whole linked list until you find a node that is pointing to null, meaning that there are no more elements from that point on, meaning that this is the last element. And we're going to use this idea to implement our queue. So before we start implementing our queue, just going to explain that we're going to have the init queue method, and the init queue method will initialize the queue, creating a head element. So our queue will always have a head node. So this is called h node. This is our head node. The head node always holds a value, and this value represents the number of elements within that said linked list, or within that said queue. Okay, and it will hold a pointer to the next element, or to the first element in the queue. And as we're instantiating the queue with no elements, it will always point to null first. And once we add the first element, this will not point to null anymore, and this will instead point to the first node that will hold the value. Imagine 9, for example, here. And 9 will now point to null because it's the only element in the queue. And this is the first node that actually holds a value inside the queue, and it is the value. And this is the pointer. So this is what we're essentially going to do. So now let's move on onto the code here real quick. So let me just create here a queue file. Queue. And let's hop onto the file. So let's start now implementing our queue method here, our queue data structure here real quick. So let's start implementing here our queue. So let's hop onto the file, queue.c, and first let's start including some libraries, stdio.h, and let's also include stdlib.h. So this one is mainly for printing, and this one is mainly for malloc. So next step, let's just create our int function, or our main function, and return 0 if everything goes as expected. Let's create our Q pointer that will point initially to null, because we haven't instantiated it yet. And now let's create here our type, that our structure for our node. And if you recall, we have a node structure. It has a value. This is the value, and it has a pointer to the next node. So this is a pointer to a node. So here we're going to create an integer value, because we're going to store integers in our queue, and we need a node pointer to our next node. And now we have to instantiate the queue. So let's first start by creating our init queue function, and we'll be passing a pointer to a pointer here, because I want to use a void function instead of returning a queue from this function. So init queue, pointer to a pointer. And first thing I want to do is create a local queue pointer here called queue that is equal to the dereference of the double pointer here, so it's easier to read the code and understand what we're doing here. So first thing we have to do is check if q is equal to null, and if q is equal to null, if q is not equal to null, because if q is not null, we have an already initialized queue. So let's say that this queue has already been initialized, and we have to early return here. On top of that, we have to now that we have checked that, we have to initialize the queue, because the queue is equal to null, meaning that the queue has not been initialized yet. We have to allocate memory for our first node, and this will be our head node of our queue. So let's create a variable here called temp. This temp variable will hold the value of the allocated memory size of queue. And now we have to check if temp equals null. This means that malloc has returned null, so it couldn't allocate memory for some reason, and this was on init queue, and we early return here as well. And now everything is fine. We can say that the value of this temporary variable is equal to 0, because this is the head node, and it holds the value of how many elements there are in the queue. As the queue is empty, it has 0 elements, so the value is 0, and our temp next will be equal to null, because it points to the next value, but we don't have any values yet. And then we just have to pass the dereference of p to be equal to temp, and we're basically done. Okay, so I'm going to use this pattern here at every end of the function, because sometimes the queue variable that we instantiate at the beginning of the function will not be pointing to the head anymore. So that's why I'm going to use this at the end of every function. We have to pass a pointer to a pointer. So now that we have initialized our queue, we have to print our queue, and let's create a print queue function. So void print queue, and we're going to pass the queue, because we're not going to write to the memory. We're just going to read the memory, and by passing a copy of our pointer here is enough to do that. So first thing we're going to have to check is if the queue has been initialized, and now we have to check if the queue is equal to null, meaning that it has not been initialized. So if it has not been initialized, we return. Else we have to check if queue next, if queue value, so this is the value of the head. If the value of the head is 0, the queue is empty. So this queue is empty. This is on the print function, so print queue. And in here we're going to do an early return as well. Next up, we have to actually print the queue in a certain way. So what I'm going to do is I'm going to loop through every item in the queue until we find the last. And every item within the queue that is not the last, we're going to print in a certain way. So while queue next is different from null, this meaning that we haven't reached the last element yet, we're going to say that we're going to print the element in this specific format, the value, and an arrow indicating that we're pointing to a value, and this value will be queue value. And then we have to say that queue is equal to queue next, because we're iterating through the whole queue. And once we reach the last element, we just want to print the value with a break line. So that's why I'm going to do print the value with a break line. because it doesn't point to anything, so there's no need to write the pointer or the arrow here indicating that it's pointing to something, because it points to null. And now we're going to write q value here as well, and our print function is done. Now we have to test it here, so let's create a print. Let's call this print q here in uninitialized q, and after we initialize the q, just to test if everything is okay. So this first print q has to print this q has not been initialized, and the second one has to print this q is empty, because the q this q is initialized, but it has 0 elements. So before we compile it and test it, we have to create the function declarations here for every function here. So let's first paste it here, and let me go down here to grab this. Also paste it in here, fix this, and we can now compile it with gcc q.c output on q. So we have some typos here, I guess. Let me check here. What is the typo? Unknown type name q. So let's get back here. Oh, because we haven't created our type name here, so we have to say that this is the q type here. So let's get back here, clear the prompt. Let's recompile it, and let's run it. So as expected, the first print says that the queue has not been initialized, and the second one says that this queue is empty. So now let's move on to creating our add function, so we can add elements to the queue. So adding elements to the queue. Let's create a break line here as well, and oops, and let's create add function. We're going to pass in our queue, and we have to pass the value we want to add to the queue. So let's say 8, for example. And every time we add an element to the queue, I want to check how the state of the queue is by using the print queue function. Let's copy this. Let's paste a few times. Let's paste 3 times. And now let's add the number 11 and the number 36. So if everything is right, once we implement our add function, our queue needs to have the following sequence. So number 8 pointing to number 11, pointing to number 36, okay? And number 8 will represent the first element in the queue. And as we're printing the head of the queue as well, the first element on the screen will be the counter of elements within the queue. So once we print the queue with number 8, there will be a number 1 pointing to number 8, meaning that we have 1 element. And when we add number 11, we'll have number 2 pointing to number 8, pointing to number 11, meaning that we have 2 elements. So and so forth and so on. So let's implement here our add function, queue with a pointer, and we'll hold an integer value. So here we also have to check if the queue has been initialized. So sorry. So we're gonna reuse this piece of code, and we also gonna reutilize this piece of code where we create a new node, where we allocate memory for a new node, because when we are adding a new node, we have to allocate memory for it, but we have to change this slightly so that the value of this new node is the value that we're passing here by the function. So now we've checked that if the queue has been initialized, we're creating our new variable, and as we always have to insert it at the end, we have to loop through the whole queue until we reach the end, and we're doing this right here in the print function. So we can reuse this piece of code. The only difference is that we don't need this print statement. We're just going to loop through until we reach the end, and once we reach the end, we're going to say that the next of the end will be the new last node. So temp represents our last node. That's why it points to null here, because there will be no element for it to be pointing to. And our last element from our queue before we add the element will now be pointing to our current new last element. And here at the end, we have to increment the value of the head, because it points the value of the head holds how many elements we have in the queue. So once we add an element to the queue, we have to update it. You could also use here via queue value plus, because before the loop, the queue is also pointing to the head, but once we reach the end, the queue is pointing to the last element. That's why if you are going to do using the queue variable, you have to do it before the loop. Otherwise, you have to use the reference of p here, because this will always be pointing to the head of the queue. So I'll use this variation at the end. That's why I stated at the beginning that we're going to use the reference of p at the end of functions that we will be adding or subtracting from the value of the head. So now that we have our add function working, let's just instantiate or create our function declaration here for our add function, and let's compile it. Add queue undeclared first. Okay, I forgot to declare the queue here as we did in the other functions. So this is our queue pointer, and it points to the reference of B. So now we're good. So now once we run the queue, this is what was happening before, and now when we're adding elements to the queue, we have one element, number 8, the first element we have added. The second element, we now have 2 elements after we add number 11, so we have 8 and 11, and now we have 3 elements, 8, 11, and 36. So everything looking good. So let's get back into the file and implement our remove function. So let's print f here, removing elements from the queue. And now we're going to implement the remove function, and we do not have to pass anything besides the queue variable, because we will be always removing from the beginning of the queue. So here we're going to print the queue after remove an element. This for the same reason as we're printing after the add, to check how the queue is after we remove an element. So as we have 3 elements, I'm going to remove 4 elements because I want to test the case when we try to remove from an empty queue. So 1, 2, 3, 4. So this is fine. So let's now create our void function remove. So we'll pass in the queue. We'll be using the same piece of code here to check if the queue is instantiated. So let's paste it in here. And we also have to check if the queue is empty, because now we're trying to remove, not add. So if the queue value pointing to the head is empty, we'll have to say that the queue is empty, and we cannot remove from an empty queue. And this is not print queue. This is remove from queue. Okay. So this is not in init queue anymore. This is in add queue. It's just a comment. It won't affect how the program works, but it affects how the output works on the console. So that's why we're fixing it. So I think everything is fine. We can now remove the element. So how we're going to do this is pretty simple. So our current queue has some elements. This is the head. Imagine we have 3 elements. This points to the first element, and I don't remember which one is the first element anymore. So the first element is 8, then 11, then 36. So imagine we have our queue here. This is 8 pointing to 11, pointing to 36, and 36 is pointing to no. This is our current queue. We always want to remove the first element. So in order to do so, we have to say that our head pointer will not point to the first element anymore, and will instead point to the second element. And to do so, we'll say that our head element, or our head pointer, will be equal to our first element pointer. So now this part has been concluded. Now our head points to the second element. We'll create a temporary variable that will store the address of our first element, and then we're going to free this element. And now our queue has the first element removed, and the head is still pointing to our new first element. Now it is number 11. And if we do this recursively, we can keep removing elements. So the second time we do this, this will not be pointing to number 11. This will be pointing to number 36. And then we're going to create a temporary variable to store the address of our new first element. We're going to free this memory, and this will be our new first element. And we only have one element now. So every time we remove an element, we also have to reduce here to subtract from our head value, because this is the counter of how many elements we have in the queue. So every time we remove it, we have to keep decreasing this value. Okay, so we keep track how many elements we have in the queue. So let's do this right now. So in order for us to remove the first element, it is pretty simple. We just have to store queue temp. So we have to store the first element in a temporary variable. So as our queue here is pointing to our head, the next of the head is the first element. So temp is now pointing to the first element, and our queue next, meaning that the next of the head will now have to point to the second element, and temp is the first, so the next of the first is the second. So now our head is pointing to the second element, and we have to free the memory from the temporary variable. And last but not least, we have to reduce or decrease the value from our head value. We could use queue value minus minus on this, because our queue is still pointing to the head of the queue. But as I stated before, I'm going to keep using this standard here. So that's why I'm using dereference of P, meaning that we're pointing to the head, and the value of the head is being decreased by 1 unit here. So let's just create the function declaration for the remove function here. Oops. Let's now test it. So let's recompile it, run Q, and as expected, we printed the stuff from the beginning, we added the elements, and now we're going to start removing the elements. So we're printing the Q after we remove the first element. So we remove 8, that's why now it has only 2 elements, 11 and 36. And then we remove one more element, remove the 11 here, that's why we have only one element, number 36. And once we remove 36, the Q is empty, right? So this is the print after we remove 36, saying that the Q is empty. And when we try to remove an element from an empty Q, it says here, this Q is empty from the function remove from Q. And we try to print it again, it's going to say that the Q is empty. So everything fine, working as expected. So let's implement our next function. Our next function will be the clear function. So before that, I'm going to add here clearing the Q, and we're going to create the clear function Q. We have to add more elements to the Q because the current state is we have an empty Q here, right? So let's add elements here to the Q before we clear the Q. We don't need these lines. We're just going to keep adding elements to the queue. And now let's add different elements to the queue. So let's add number 12, number 89, and number 27, for example. And once we clear this queue, it will have the effect of running the remove function as many times as we can until the head is pointing to null, right? So implementing the clear function is pretty simple. So the way we can do this is simply by creating a function that iterates in a loop, calling the remove function until the head is pointing to null. So let's do this. So let's create a function called clear that takes the pointer, and in here let's create here the Q pointing to our dereference of P, and while our Q next is different from null, meaning that this will check if our head is pointing to null at some point, and we'll keep removing elements until our head points to null. And now we just have to call the remove function on our pointer to the pointer, and this will do the job, right? So now we just have to copy this and paste it. And why am I not adding these checks here in this function? Because once we're calling this, every time we're calling this, these checks are being done. So we don't have to redundantly add these lines of code within this clear function because the remove function already has these checks, okay? So let's get back here and let's try to, oh, I forgot to add the print function at the end, right? Yeah, so right after we clear, we want to check the state of the queue. So once we clear the queue, this print queue has to return the queue is empty, right? So let's recompile it. We haven't created the function declaration, so let's void clear queue. Let's clear the screen, recompile it, and run it. So this is the old stuff, right? Until we remove elements, we've seen this before, but now we're re-adding elements to the queue, so the queue was empty, and now we add number 12. That's why we have one element, number 12. We add number 89, 2 elements, number 12, 80, followed by 89, 3 elements, number 12, 89, and 27. And when we call clear queue and print it, the print says this queue is empty on print queue because the clear function basically removed every element in the queue. So now we have to implement the free queue. But before that, let's implement the peek method as well, because it's really easy to implement the peek method. And we can even implement it right above here. So void, it's not a void, it's an integer, because peek method returns the element at the beginning of the queue. So queue, p, and we can only return elements if the queue has been initialized and it has elements. So on top of that, we also have to copy this. So let me paste it right here. So if we have elements in the queue and if the queue has been already initialized, we're going to return the first element. So we're going to return queue value. This is pretty simple. And we can check if this function is working properly by printing it in the main function here. After every time we add an element, we can create a print statement printf picked element, so we can check which element we're picking, and we can call pick function on the queue. And we don't have to pass the queue here like this because we're only reading, right? So let's fix it on the original function. So here we only need one pointer queue, and we do not need this line because we're not writing to the memory, we're just reading the memory, so this will work. And let's go back to the top of the file, and where is it? Line 20. Let's copy this line and paste it every time we add an element. Oh, sorry, this line. Every time we add an element, we're going to peek. And as we're adding elements to the end of the queue and we're picking elements at the beginning of the queue, this peek element will always return 8 until we start removing elements. That makes sense because we're not changing the first element, right? When we add, we're keeping the first element as number 8. And once we start removing elements from the queue, so once we remove element from the queue, now this will peak number 11, and now this will peak number 36, and now this will peak something else, and we have to return something if it doesn't find anything, if it is empty, and here the same thing, right? So let's simply fix the function again because we're returning nothing in a function that has to return something, and let's make it return -1 as the standard if it fails, right? So let's comment here at the top, returns -1 if it fails. So that's why we're returning -1. If -1 is the top element of the queue, this will overlap and will obviously return -1 as well as the value, but the difference is we will not have these print function sentences here, and this is how you can differentiate if we're returning -1 from the queue element or from an error. So if it has the message here, peek from queue, right? So if we're returning peek from queue and return -1, it means that the queue is empty and we return -1 because it failed. So let's just go back to the top, and same thing here. We're not going to add the peek function here because it will always be peeking at 12. So the same thing that happened here will be always peeking at 8. So let's test this function now. Let's clear, let's recompile it. And I forgot to the function declaration once again. Let's get here the function declaration. 13, paste. And now we can recompile it and run it. Same old stuff until we removed elements, and now we can check that we have added the peek function right here. So peek element 1, 2. Oh, I am returning the head element. Sorry. We have to fix it on the peek function. We don't return the head value, right? Because if we return Q value here, we're returning the value of the head. We have to return the first value. So the value of the first element. That's why we have to return the next value. Okay, so let's fix it. Now we're done. Let's go, and here we go. So now we're peeking at number 8. That's the first element, and then when we add 11, it's still number 8, and when we add 36, the first element is still number 8. And when we start removing elements, we remove 8, the first element becomes 11. That's why we peek 11. When we remove 11, the first element becomes 36. That's why we peek 36. And once we remove 36, we peek -1 because this queue is empty. Peek from queue. So it says it returned -1 because of we're trying to peek this element from an empty queue, and the same thing happened down here. And here we're just adding elements as we tested before. So 1 element 12, 2 elements 12 and 89, 3 elements 12, 89, 27, and then we clear the queue and it prints this queue is empty. So now the only method we're missing is the free queue method. So what we have to do here is let's first re-add elements to the queue. Let's do the same thing over here. And now we're going to add different elements to the queue. Let's add 67, 23, 71, and let's add some more elements. Print. Let's add 5 elements in total. Let's add element number 2 and number 107 for some reason. So let's delete this peek element because it will always be peeking at number 67 because we're just adding elements to the queue. And now we are going to call the free queue method. So free queue. And now let's call free queue on our queue. And the only difference between FreeQ and clear is that clear only frees the memory from the elements within the queue. FreeQ will also do this clear, but on top of that, we will free the element of the head, right? So how we can create this free function is by declaring the free function, calling the clear method, and just freeing the memory of the head. And once we print Q after we free the queue, we expect not only the queue to be empty, but the queue to be uninitialized because we're freeing the head of the queue, right? And the queue will now be pointing to the queue pointer, or the header pointer will now be pointing to null because there's no head anymore. We're freeing the whole memory from the queue. So let's do this. Let's create this free queue function. We're gonna pass in the queue. The only thing we have to do here is call clear on P, right? Because we're going to free every single element within the queue. And now we're left with the head of the queue. And just to make things a little bit more easy to read, I'm going to reuse this queue. So this queue is pointing to the head. And as Q is pointing to the head, we have to free this element, right? So Q is pointing to the head. We're going to free Q. And now that the pointer to the head has been freed, there's no more memory here. There's no memory address here. We're pointing to null. So we have to say that the dereference of P is now equal null. And let's create this function declaration on top before I forget it. Once again, if we clear the screen, let's recompile it, run it, and there we go. So let's just recap. So first, we print an uninitialized queue. So that's why it says printing an uninitialized queue. So then we initialize the queue, but the queue is empty. So that's why it prints the queue is empty. So we then start adding elements to the queue. So we add number 8, and we peek it, meaning that we're peeking the first element of the queue. So that's why we peek number 8, and we have one element, number 8. Once we add number 11, we have two elements, 8 and 11. And once we add number 36, we have three elements, number 8, 11, and 36. And the peeked element remains the same because the first element of the queue hasn't changed. So now we start removing elements from the queue. So we remove the first element, so we remove number 8. That's why the peaked element is now number 11, because the queue has two elements, 11 and 36. Then we remove another element. Now the queue has only one element, number 36. That's why the peaked element is number 36. And then we remove it again, and we print, now the queue is empty, so we pick an element from an empty queue. So that's why it prints here, this queue is empty, so we pick from queue. And then we try to remove from an empty queue, that's why it says the queue is empty, remove from queue. And then we try to pick again from an empty queue, that's why it says here, pick from queue, the queue is empty, and returns -1 again. So now, we're gonna re-add elements to the queue to test the clear function. We add number 12, 89, and 27. So now the queue has three elements, 12, 89, and 27. And once we clear the queue and print it, it only removes all the elements from the queue, but it keeps the head. So the queue is essentially empty. So that's why the print says here, this queue is empty. And then we re-add more elements to the queue to test the free queue method. We add 67, 23, 71, number 2, and number 107. That's why the final state of the queue has 5 elements, the ones I've just stated before. And when we free queue, we not only remove every single element from the queue, but we also free the head of the queue. And that's why when we print it, it says this queue has not been initialized, because the pointer that was pointing to the head of the queue is now pointing to null. There's no head allocated anymore. So there are no more nodes in this queue. So that was it. I hope it was helpful. I hope you could understand a little bit. If you have any questions, you can post in the comment section down below. In the future, I'll be bringing more videos about how to create more different data structures in C, like graphs and hash tables. And yeah, that's it. Thanks a lot for watching, and see you next time.